So here's how to use the root method to solve differential equations. Before I go any farther, you should know that you need to have a solid grasp of basic algebra to do this. That means you need to know about the quadratic equation, basic trigonometry, imaginary numbers, and of course calculus. Strictly speaking, you don't need to do any calculus to do this method, but of course differential equations is all about calculus. Now, the root method is sometimes called the eigenvalue method, but I suggest you avoid this terminology because there is another completely different eigenvalue method, and you don't want to get the two mixed up. The root method works for differential equations in this form. They must be linear, they must have constant coefficients, and they must be homogeneous. Now, it is possible to use the root method to solve non-homogeneous equations that are otherwise in this form, but there's a whole process involving this and another method, the method of undetermined coefficients. I won't be getting into that. Now, this is a second-order equation. The root method works for first, second, third, whatever order you want equations. Whenever you solve a second-order equation, there are four possible outcomes, and I'm going to do four examples where I show you one of each of those. And then I am going to summarize the results both for first and second order equations. And some of you might want to just skip ahead to the summary and only come back to these examples if the summary is not entirely clear to you. Now, the first step in this method is to write something we call the characteristic equation, also sometimes called the auxiliary equation. Essentially what you would do is erase all these y's and then replace them with powers of r. Second derivative gives you an r squared, first derivative gives you an r, and then if there's no derivative here at all, then there is no r here, and it's easy to mess that up. R is what we call the root, or eigenvalue. Now, textbooks will go on for pages and pages trying to justify what I'm about to show you, but I'm going to skip a lot of that and just show you the bare minimum that you need to actually solve the problem. If anyone wants a more in-depth explanation, leave a request in the comments down below, and I'll look into it. So what do we do with this? We want to find the roots. If you're able to factor this quadratic, go for it. If you have difficulty factoring, you can always use the quadratic formula. Now you can see what we have here is two roots, both of which are real numbers. We call these distinct real roots. In this case, the solution looks like this. So here's our general solution to the equation, which features a couple of exponential functions. The roots show up in the exponents. There's -1, there's -5. These coefficients could be any number you like, as long as they're constants. Now, if C1 happens to be equal to 1 and C2 is equal to 0, then your solution will just be e to the power of -x. Similarly, if C1 is 0 and C2 is 1, then e to the -5x will be a solution. So each of these is a solution by itself, and then any linear combination of the two will also be a solution. And with a second-order equation like this, you should always expect to see two linearly independent solutions. Here's another example. There's the characteristic equation, and there is the solution. There's only one solution this time. So we have repeated real roots. Now, strictly speaking, the root isn't really repeated because there's only one of them, but the factors that give you the root are indeed repeated. There are two of those. The solution looks like this. There's one solution all by itself, but we need two linearly independent solutions. How can we do that when we only have one number to put up in our exponents? Here's how. You multiply by x. Again, the coefficients could be anything. This is a solution all by itself, and this is a solution all by itself. The exponential function together with x. X times e to the 3x will indeed be a solution of this differential equation, and of course that's not immediately obvious. But if you take the first and second derivatives of this and substitute them into here, they will cancel out and give you a 0, regardless of what coefficients you have there. So here's our next example, together with the characteristic equation. R squared equals -9, so r equals plus or minus 3i. we have to bring in an imaginary number because we're taking the square root of a negative. These are imaginary roots. And the solution looks a bit different. It has trigonometric functions. Again, the coefficients can be anything you like. So sine of 3x all by itself is a solution. Cosine of 3x is another solution. Any linear combination of the two is a solution. One more example. Here's our differential equation. Here's the characteristic equation. And I'm going to use the quadratic formula to solve this one. And there's our solution. Once again, we need a plus or minus I because we've got a radical with a negative, but we also have a real part to the solution. So these are complex roots. And the solution looks like this. Again, we have two linearly independent solutions, and any linear combination of those two is also a solution. Notice we have an exponential function, which has the real part of our root up here in the exponent. And then we have this trigonometric function that has the imaginary part inside of there. Now I should mention that this radical is not really significant. You can get real roots with radicals as well. Now for some reason, most textbooks and professors don't like to write it this way. They prefer to write it this way instead. They just factor out the exponential. So I just showed you 4 examples with 4 different outcomes. Most books and professors will tell you that there are 3 possible outcomes because they lump these two together. And I think you can see that in a sense, this is just a special case of this. If the real part of your solution is equal to 0, then you have a 0 in your exponent. E to the power of 0 is 1, and then your solution looks very much like that. So let's summarize. For a first-order differential equation, you can write your characteristic equation thusly. Wherever you see a prime, you put a power of r, 1 prime, r to the power of 1, no primes, no r's at all. You solve for r, which in this case will be that, and then your solution is always going to look like this. It's an exponential function with your root up there in the exponent, and then some arbitrary coefficient. With a little practice, you might be able to just look at your equation and see the solution right away. Here's the second order case. It's just like the first order case, except your second derivative gets you an r squared. There are various possible results. Your roots could be 2 real numbers that are different from one another. We call those distinct real roots. If that's the case, the solution looks like this. You get a couple of exponential functions, and the roots are up there in the exponents. What happens when you have a real root, but there's only one of them? The solution goes like this. You get a couple of exponential functions, just like before. They have the same root in the exponent, but one of them needs an extra x. Last but not least, we have complex roots. They always come 2 at a time. So you get an exponential function together with some trig functions. In the special case where a is equal to 0, this exponent is 0, e to the power of 0 is 1, and then you have a simpler expression that just has trigonometric functions. If you have trouble following any of that, then go take a look at the examples. If you would like to see me give the same treatment to third-order equations, leave a request in the comments down below and I will look into it. Thank you very much for watching. Please like and subscribe. If you are craving more differential equations fun, there's a link to my playlist on the subject. Also, if you're interested in being tutored online by me personally, I am available until further notice. And you can find a link in the description down below with more info about that.